Let's take a look at this circuit. We're going to use Ohm's law and KVL and KCL to find what they're asking for in the problem. Sometimes, a lot of times with these problems, you aren't able to just immediately find the things that they're asking for. And so I often go about it as thinking that, well, I'm just going to, quote, solve this circuit. In other words, find out everything I can find out about this circuit. Or, just figure out what I can find. And once I find something, then say, okay, is that enough to get me what I need? So always a good idea of how to start is say, well, let's start with either KVL or KCL, and you can choose one and see which one you like. I like KCL. I mean, we use both, but I like KCL, and I like it because on this particular circuit, I already have labeled for me I1 and I2 coming out of this node right here, and coming into this node, I have 1.5 amps. So this node is already perfectly set up for me to use KCL. So KCL would tell me that the sum of all the currents coming in has to equal the sum of all the currents going out. So at that node up there at top, I would say 1.5 amps equals I1 plus I2. All right, so I've got one equation with two unknowns. If I continue to have just two unknowns, then I will need to have one more equation before I can solve them. And so now I want to use KVL. So doing KCL again won't help me, because if I were to try to use KCL again, say at this node, well, what would I have at that node? At this node, I'd have that the currents coming in are I1 and I2, and the current going out is 1.5. Well, that doesn't help me because that's exactly the same equation that I had before. So I need to use KVL and not KCL. Now, KVL on the left-hand loop is a little bit harder, because with KVL, what you're looking for is the voltage change across each element. And I don't know the voltage change across this current source because I don't know the resistance of that current source. Now, eventually, I have to find the voltage change across that current source because that's one of the things that's being asked for. But I don't know it right now. And so KVL on the left-hand side would be a little more tricky, as would KVL around the whole loop, because to use KVL on that, I'd have to solve for some other stuff anyway. So I'm going to use KVL on the right-hand loop. Now, I want to make sure that I'm going around the loop in the same direction every time, and so I'm looking at the change in voltage across each element as I'm going around this loop. And when we do this, we use the passive sign convention, meaning that if I have a resistor and I have a current going into that resistor, then and my loop is going in this direction, I'm going around in that direction, then I'm going to call this the positive side and the negative side of the resistor, and I am going to come up with a positive voltage change across this. I've always found that a little odd, and you'll see that when you do something similar in your physics class later this semester, they're going to do it. They're going to use the opposite convention. It is just a convention, but keep that in mind because it may confuse you when you see them doing it. You can always continue to do it your way. It doesn't, as long as you're consistent, you're fine. So if the current is labeled as going in the same direction you're going in, then we would call that current, quote, positive, meaning I don't change its sign. Whatever sign it has, that's what I'm going to use. So if it's labeled I1, then I call it I1. Now, on the other hand, if I had I1 going this way, and the loop that I'm using for my KVL is going this way, then I would use a minus I1. So let's say this resistor is R1. If I were doing KVL in this first scenario right here, the voltage change across this resistor, remember Ohm's law, V equals IR, the voltage change across this resistor in scenario 1, so delta V, would be I1 R1. In the second scenario, delta V would be minus I1 R1 because my loop is going in the other direction. Now, neither of these things tells me whether or not my current is positive or negative, or in what direction my current really flows. It's all relative to how I have it drawn. So in I have the current drawn, I1 is defined as going to the right. So if it's defined as going to the right, then I'm saying going to the right means that I have I1 without a negative sign. Okay, so those were a lot of words before I set up my KVL equation. So going across each resistor, I'll want the voltage for going across that resistor. And to get the voltage across each resistor is going to be I times R. It'll be the current times the resistance. So I'll start right here. So I'm going to start going around my loop in the clockwise direction from the little yellow dot I did right there. So going across that first resistor, my voltage change is I2 times 150. Now I2 doesn't change as it continues on along this path because the 250 ohm resistor is in series with the 150 ohm resistor. So the same current flows through it, so I also have I2 through the 250 ohm resistor, and it's also going in the direction of the loop. But then as I come up over here, I'm going up this middle branch, and I1 is going down that middle branch. And so if I'm using I1 as labeled, which I am because I've already used it in the first equation, then I need to write that voltage change as minus I1 times 100 equals 0. So now I have 400 I2 minus 100 I1 equals 0. Now let's make these, let's just go ahead and say that this is same as saying 100 I1 equals 400 I2, or I1 equals 4 I2. And then I can plug that in to this equation. 1.5 equals I1 is 4 I2, so 1.5 equals 4 I2 plus I2, or 1.5 equals 5 I2, or I2 equals 1.5 divided by 5, and 1.5 divided by 5 is 0.3 amps. So I2 is 0.3 amps. Now I1 is 4 times I2, so I1 is 4 times 0.3 amps, which is 1.2 amps. Okay, so now I have found the currents I1 and I2, so I've done part A. Alright, now part B wants me to find the voltage VO. Well, how do I do that? I can't use Ohm's law because I don't know the resistance there. What I do to find voltages of things that I can't just use directly Ohm's law on is I look to see if they're in parallel with something, because things that are in parallel will have the same voltage across them. And if I look at my current source right here, right, so here's my current source. If I look at my current source and I look at this resistor right here, then I see that they're connected right here with nothing in between them. They're connected right here with nothing in between them. So these have to be at the same voltage, whatever voltage they're at, and these have to be at the same voltage, whatever voltage it's at. So we know that the voltage change across these two elements has to be the same. So if we can find the voltage change across across this 100 ohm resistor, that voltage change will be the same as the voltage change across the current source. So if I look at this top voltage minus the bottom voltage, then what current is, so I1 would be the voltage where I'm starting, which is V1, minus the voltage where I'm ending, which is V2, over the resistance. And so V1 minus V2, that, if we look at it, that would be the same as V0, because V0 is when we label something with a voltage and we have a plus side and a minus side, that label means, so the label means the voltage at the plus side minus the voltage at the minus side. And we just said V1 is the voltage at the top, V2 is the voltage at the bottom. So I1 equals V0 over 100, or I1 was 1.2 equals V0 over 100, and then that gives me that V0 is 120 volts. All right. Okay, now part C is to verify that the total power developed equals the total power dissipated. So sometimes you have to be careful to determine whether something is absorbing power or supplying power. In this particular example, we don't have to be very careful because we know that resistors are always absorbing power. That's what they do. As they resist the flow of current, they are absorbing power. And current sources supply power. And not only that, it has to in this instance because there's nothing else in this circuit that could be supplying power. And so the only thing that could be supplying power is the current source, so it has to be supplying power. So we know that the current source is supplying power and the resistors are absorbing power. But we're going to make sure that it works the way we think it does anyway. So let's label what we know. We know this is 120 volts right here. Or if I call this ground, so if I measure things relative to ground, then I would say the bottom is 0, the top is 120 volts. It's also true here. That would be, the voltage would be 0 there, and the voltage would be 120 there. We know that current 1 was 0.3 amps going down in that direction. And we know, oh no, current 1 was 1.2 amps going down, and I2 was 0.3 amps going in that direction. Now what we don't know, so we do know the voltage across the 100 ohm resistor. We don't know the voltage across the 150 ohm resistor or the voltage across the 250 ohm resistor. They're going to be different because they're in series, and things in series will have different voltage drops, usually. So we're supposed to be finding the power. The way I remember power is P equals IV. I don't know why, but I have a hard time memorizing things, and so I only have like just a handful of things memorized. So there are 3 ways that we can write P equals IV, or to solve for power, because we also have Ohm's law that V equals IR if we have a situation where we can use Ohm's law, like you have a resistor. Like we can't use Ohm's law if we don't have a resistor. And so I can substitute IR in for V and also get that P equals I squared R. So that's handy if I don't have the voltage. Or I can say that I equals V over R, and I can substitute that in, and I get V squared over R. And that can be helpful sometimes as well. Okay, so let's find the power for each of our sources. So for our current source, notice I'm going to use P equals IV. And when I do that, if my current is going in this direction, and when we're looking to see whether or not we want to use a positive or a negative voltage in our equation right here, we look at what side of our source we're entering. The current is entering into the negative side. So that means we're going to write a negative voltage here. So we have our current is 1.5 amps, and our voltage is a negative 120 volts. and 1.5 times 120, so that gives us negative 180 watts. And so we would say 180 watts supplied. You don't say negative 180 watts supplied. Your answer can either be negative 180 watts, or you can say 180 watts supplied. You don't say negative 180 watts supplied. Okay, so now let's look at our resistors. So we'll start with our 150 ohm resistor. We know the current and we know the resistance. So rather than solving for the voltage, which is what I usually do, we'll just go ahead and use that formula. So P equals I squared R. So our power is going to equal I, which was 0.3 squared, times R, which is 150, and I think that is 13.5 watts, and that is positive. And now for our 100 ohm resistor, our power, we could use either IV, or we could use I squared R. I'll use IV because I know the voltage. So the current is 1.2. And my voltage, notice I'm the side that I'm entering, when I look the way my current is labeled, the side, well, it's a resistor, it has to be positive, I mean, but it is, it's entering into the positive side of it. So 1.2 times 120, which is 144 watts. And lastly, we'll look at our 250 ohm resistor. And for this one, it's easier to use P equals I squared R because we don't have the voltage. Again, the current is still I2, so it's 0.3 squared times 250, or 0.09 times 250, and that gets me 22.5 watts. Now, if everything worked as we expected, then the power absorbed should equal power supplied, and that would be 13.5 watts plus 144 watts plus 22.5 watts, and I'm pretty sure that equals 180 watts. And so good, it worked. We probably did all of our math correct.